John works at the interface of convex optimization, information theory, statistics, and privacy. And recently he's been sort of coming back to privacy, also doing some more applied things to privacy. So excited to hear what he has to tell us.
Okay, thanks, Guy. Right, so yeah, unfortunately I can't quite talk about the applied stuff yet because it's still one of the companies local to Stanford is working with me on this, but I can't tell you which one or what we're doing yet. Give me a couple weeks and I'll be able to answer that, but just not yet. Anyway, so let me jump in. So this is based on joint work with my student Feng Ruan, and I'll also talk about some older work. So the starting point is going to be the motivation. So you guys probably don't need too much in terms of motivation. You know, why do we care about privacy? Well, because we have all this data we collect, genomic data, drug use data, financial information that you might want to keep private from other people so they don't exploit it. But of course, if good researchers get a hold of this data, then there's a lot of potential benefits. Maybe we infer things about biological bases of disease. Maybe we get better epidemiological control. Maybe we can get better economic policy making. And so kind of the questions I want to try to start poking at in this talk are going to be sort of along the lines of what are the fundamental trade-offs between privacy and statistical utility. Okay, how do we understand them and how do we trade off between them? And I've been doing work on this for a couple of years now, and I'll go into depth on one or two things, but I also want to give kind of an overview of some of the different directions here and also just introduce you to the basic concepts in privacy in case you guys haven't seen them. So let me motivate a little bit why we might care about privacy. So example one comes from biological applications with microarray data. So what is a microarray? It's basically a collection of expression levels for a bunch of different genes, right? And now you can ask, okay, so you'd say, okay, let's suppose I collect microarrays from a bunch of different people, and then I hand out a histogram of the number of times different genes were expressed, right? Or just like the mean expression levels of the different genes. Then you think, well, that should be reasonably safe. Okay, so here's kind of a funny example. Here's gene 1 and the number of times it was expressed up through gene D and the number of times they were expressed, right? Now somebody comes to you, or maybe I'm an insurance company and I want to know, was this person I'm trying to insure in this data set of cancer survivors or something like this? And now I want to ask, was a person in this study? So here's one person's genes, and then maybe they were in the study, maybe they weren't. They have a lot of counts that are sort of genes appearing in places where there were a lot of counts. Maybe they were, maybe they weren't. Don't know. Okay, here's a person, and this person, has sort of genes appearing in these places, say some rare genes where they only appear once in my entire study, and this person has all of them, and you say, oh, these are rare genes, this person's got all of them. That's kind of suggestive he or she was in the study. And then here's a person who's missing an expression on, say, this orange one, which I know was on everybody in the data set, and now I know definitely this person wasn't in my data. Okay, so I've basically I've somehow pierced through the idea that taking just aggregate statistics gives me some protection. And actually, in a sort of more sophisticated way, Niels Homer and colleagues in 2008 did this, and it caused the NIH to stop releasing genetic data for a couple of months back in the late 2000s. All right, so there was pretty significant consequences to this kind of breach. Example 2 is the Netflix prize. So you guys are familiar with the original Netflix prize. There was supposed to be a second Netflix prize where they were going to release more information and let you try to give better movie recommendations. And then there was this woman who sued Netflix and said, well, Netflix spilled your Brokeback Mountain secret. And basically she claimed that they had outed her as being a lesbian and filed suit, and then Netflix just canceled the contest because they were like, nope, we're done with this. No longer releasing any data. Okay, just because, I don't know if you guys remember Brokeback Mountain. I went and saw this with a really good buddy of mine by ourselves. I think people gave us some funny looks. I was wearing a rainbow jacket at the time, so that might have been part of it. But anyway, there were non-trivial consequences to these kind of privacy issues. So, all right. So then, hopefully you're convinced that privacy is an issue. Let's talk about how we might actually give some kind of mathematical formalization to privacy. All right. So how should we define privacy? So what we're going to do is we're going to say, all right, data is coming in, x1 through xn. These are x1 through xn are always going to just be raw data, non-privatized, but it's what you want to sort of prevent disclosures about. All right? It's going to come in, and what's going to get spit out is some mechanism. Excuse me. In the first part of the talk, my mechanisms will be M. I'm going to switch this a little bit in the latter parts of the talk to give kind of a slightly more information theoretic flavor. But so data is going to come out in some mechanism M. Okay? It's going to spit some random thing out about your data. And then, so what do we want from privacy? Okay, so one version of a definition of privacy might be the following. Whether or not I participate in a study, the results of the study should be about the same. Okay, because then, whether I participated or not in the study, people don't, nothing changes about the study, so no one learns any particular information about me. All right, that seems like a reasonable desiderata. Okay, another version. Let's do a hypothesis testing version. Say, suppose a bad guy knows everybody in a particular data set except for the last person. And he's trying to decide whether the last person is me or whether it's Sasha. Okay? Then I want a guarantee that, even given sort of the output of my mechanism, whatever scheme, whatever data thing I'm doing, the adversary can't actually test, or at least can't test with high accuracy, whether that last person in the data set was me or was Sasha. All right, that's fairly strong, but it's kind of, if I gave you that guarantee, you'd probably feel pretty safe, right? You say like, okay, yeah, that's pretty private. So another version is, maybe I'm a Bayesian, and somebody has a 50-50 prior that the last person in the data set or that the data set itself is X or it's X prime. The last person in the data set is me or Sasha, 50-50 prior. Then I want to guarantee that even after my sort of adversary observes the output of my scheme or my learning system or whatever, that his beliefs are still pretty close to 50-50. Okay? So the nice thing about this idea, this kind of Bayesian perspective, is by encoding, say, some prior knowledge into my adversary, basically, if I have a privacy definition that satisfies this, then this prevents side channel attacks. Right? So if you think about it, I can encapsulate any information the adversary might know about me from other sources by, say, going through census records or by coming to my house and looking at things around my house or going through my trash or whatever. I can encapsulate that all in this sort of prior beliefs, how certain he is about me. I just want to guarantee that no matter what happens, my adversary's beliefs can't change that much. All right, so these are sort of, I think, you might say that, if you satisfied any of these or all of these, you'd feel like, okay, this is a good definition of privacy, at least in some, this is a reasonable definition in some kind of semantic way. Okay, so the cool thing is that in 2006, Cynthia Dwork, Frank McSherry, Kobe Nissim, and Adam Smith provided a definition which we call differential privacy. Many of you have probably seen this, but it says that a mechanism M is epsilon differentially private if, for any pair of data sets that differ in only one entry, the probability that the output of the mechanism belongs to some set A, whether you applied it to data set 1 or data set 2, the ratio of these probabilities is less than e to the epsilon. All right?
For every A?
For every set A. Oh, yeah, sorry. That's also for all A. I can't edit the slide on the fly. So for all sets A, for all data sets differing in only one entry, you have this inequality. Okay? And there are weakenings of this, but let's just roll with this. And so it turns out that this is basically equivalent to all of our desiderata. Okay, so this definition and our 1, 2, 3 desiderata for definitions of privacy are more or less exactly the same thing. All right? And you can make this rigorous in a number of ways. One way that, so here's one version of making this rigorous. So basically, so let's assume epsilon is less than 1 for now. Then we can say that the following two things are equivalent for any test you might come up with and any possible pair of samples, x1 and x prime, sorry, x and x prime, that differ only in one element. You can condition, no matter what output M you observe from your mechanism, the probability that you can test, test that data set 1 came or data set 2 came, your probability of making mistakes is at least 1 minus epsilon. even, no matter what the output of your mechanism is. And then this is equivalent, it turns out, to saying that the mechanism is differentially private. There's a, I mean, there's a multiplicative factor, say like 2 on the epsilons that have to change from 1 to 1, but they're from the 2 different schemes, but they're basically the same thing. So no matter what output of the mechanism you get, you can't test whether or not it was data set 1 or data set 2. All right. So any questions on the definition of differential privacy? So this has become basically the accepted definition of what it means to be private for very good reasons, because it gives you all these protections. OK. So let me go through a few examples just so we've seen them and we kind of understand roughly what the standard approaches are here. So the typical game in privacy is that you want to release some function, f of your data, x1 through xn. All right, and somehow the simplest way to do this is in step 1, you compute what's known as the sensitivity of your function. And sensitivity is a word that people made up, but if you took math classes, you would know that this is just the Lipschitz constant. So we have other words for that. I should probably stop in this direction. So the sensitivity is just, if I'm going to change one element in my data set, how much can my function possibly change? Okay? And then step 2 is, well, what I do is I take my function, I evaluate it on my data set, and then I just add noise that scales with this sensitivity. So the more sensitive my function is to input changes, well, the more noise I add. It's kind of intuitive, right? And that's what I'm going to do, right? So the picture is, if, here are my 2 functions, f of x and f of x prime. If the most they can move, if they're not that sensitive so they don't change very much, well, then we only need to add a little bit of noise, so that, OK, there's enough overlap between these, you're going to kind of get confused if you just add a little noise. Whereas if when I change one entry, f of x and f of x prime move a long way away, we're going to need to add a lot more noise. It's sort of intuitive. OK. So then the standard classic mechanism for this is basically what's known as the Laplace mechanism. So I said, OK, we're going to add noise scaling with the sensitivity. Well, the typical choice is to add Laplace distributed noise. Okay, so the Laplace distribution is just, I have epsilon as my differential privacy level. Then I'm going to add noise with density e to the minus epsilon times the absolute value of w. Right? So the nice thing is you can see that the ratio of this is always going to be bounded by e to the epsilon. So I have either f of x prime, f of x, and then I have just 2 different Laplace distributions peaked at the true values f of x and f of x prime. All right, and then of course, you can fairly straightforwardly just prove that this is an epsilon differentially private scheme by just saying, OK, well, the probability that my mechanism outputs mu, well, that's equal to the ratio of the densities divided by their sensitivity. We just go through this. Well, the most this is going to change is delta f, and then I get e to the epsilon. Okay, just a quick 3-line argument. You get that this is a differentially private scheme anytime you can give a bound on how sensitive your functions are to changes of one person in your data set. Okay. All right, so that's the Laplace mechanism. So sort of the typical standard examples here are something like I want to release histogram counts. I want to release something like gene expression levels, how many times different genes were expressed. So then I've got some histogram that's got m different buckets. Here's one data set. I get another data set. It's got one more entry in, say, the second bucket here. So the sensitivity of the histogram is, well, 1, right? The most, or 2, depending on how you count. 1 or 2. One person comes in, that removes a count from one place, puts it somewhere else. So your sensitivity is 2. And then what you're going to do is your mechanism is just going to add noise to each of the counts, which then the magnitude of the noise should be proportional to 1 or 2. Right? And so that's what you get. So you basically just release a bunch of perturbed counts. You take your histogram. You add a vector of Laplace noise. And that guarantees you differential privacy, for these counts. Right. So many of you may have seen this before, but this is kind of the standard story for how we do, simple privacy-preserving schemes. All right, and there's this huge literature now on differential privacy. I'm not touching much of it at all, but there's huge numbers of algorithms designed for lots and lots of problems: histograms, ranking, solving machine learning problems, principal components. So there's a whole literature on this. There's also a nice literature developing. Okay, what happens when we take a data set and 3 people sort of do differentially private analyses on it? Or you do a differentially private analysis like 6 different times. Like, you can compose these things together and still you can maintain certain privacy guarantees. So there's a nice literature on this. Then there's recently been kind of a set of papers working on how do we weaken notions of differential privacy to allow more sort of powerful inferences and more powerful estimation. So there's a whole literature on weakening these things. I just wanted to sort of set us up. They all end up boiling down to things close to differential privacy. But I just wanted to sort of set the stage for what the standard approaches are. Okay. Questions? We're good. All right. So now what I'd like to do actually is move into a slightly stronger privacy model than sort of this standard differential privacy, right? So what the model I'm going to use now is what's known as local privacy. And in local privacy, basically providers of data don't even trust the data collector, right? Because they don't know the data collector from a hole in the ground. They're like, okay, I have no idea if you're going to keep my data private. So what's the game? Well, basically, you start off with your data. X1 is person 1, X2 is person 2 through Xn. And then I have some kind of estimator or quantity I want to compute about their data. But what I'm going to do is put this barrier between these people and whatever I'm collecting. And so instead of X, whoever's collecting the data gets to observe Z, where Z is some obfuscated version of X. Okay, and so the way I'm going to always write this for the rest of the talk is I have X is going to go through a channel, and I'm going to represent that channel by Q. Q is always going to be a channel, and then this Z gets spit out. Okay, so X goes through a channel, Z gets spit out, and then the statistician or whoever has to estimate the quantity of interest based on these Z's, right? And if we want to be fully general, we'll allow sort of schemes where you can change the sampling mechanism from X1 to X2 to X3 by, there's a channel, and we can change the sampling mechanism from X1 to X2 to X3. So Z2 may depend on Z1 and X2. Z3 may depend on everything in the past. Zn may depend on all of the other Z's as well as this guy. Because this is going to allow you to develop better mechanisms and more efficient algorithms and more powerful schemes. Okay, so this is going to be the setting for the rest of this talk. Is you don't trust me, I'm collecting data, you want to make it private before it gets to me at all. So any questions on this picture?
What do the horizontal arrows between the Z's actually correspond to?
What do the horizontal bars between the Z's actually correspond to?
With respect to releasing your private data.
Yeah, so what it means is that, so person 1 comes along, and you get to have Z1 is drawn from basically Q of dot given X1. Okay, then when person 2 comes along, I get to change sort of this random sampling scheme. So Z2 is going to may be drawn from some channel that depends on both X2 and Z2.
So you're giving the person the whole previous Z.
Yeah, the person can see all the previous Z's, or since I'm the statistician, I am allowed to choose that. I can choose whatever channel we're using as long as it's going to guarantee some kind of privacy. Sorry. Yes, thank you. That would be a weird probability distribution. Z1, right? And then Zn, I can change my channel to depend on Xn and Z1 up through n minus 1. Right, so that's the game. I mean, it's just going to allow me more powerful algorithms. It turns out that if you kind of force each of these to have the same, say, marginal distribution or same conditional distribution, then it's actually pretty hard to solve most problems. So that's the game. Okay. All right, so basically the picture is that, here's me collecting your data, here's you with your personal data, and we're going to obfuscate it before I get to see it. And we're going to use typical differential privacy guarantees, basically the probability that the statistician or policymaker can distinguish me from Sasha, even if he knows we're the ones giving the data, is going to be less than 1/2 plus some epsilon. Okay, so it's very close to 1/2, just 50-50 chance for him. All right. Okay, so sorry. So you might ask, why would we ever actually care about this model of privacy? I mean, one reason is like survey sampling or things like this, but another one that's really important these days is, we have phones, right? We all have cell phones in our pockets. These things are constantly collecting data on us, but some major cell phone providers, specifically Google and Apple, want to fit models of what you're doing on your phone, say to predict the next word you're going to type, or give you suggestions for where to go to dinner or whatever. But for good reasons, they are starting to be a little bit sensitive about the fact that they are collecting all of the data about you, right? So now we want to start to fit these models or fit these prediction schemes privately. So you want to have an image classifier or some text translator or some speech recognizer, but you want to make sure that people's data you're collecting stays private. And this could be both because you have philosophical reasons for being private or because you don't want the government going in and sniffing around in your private data, which is certainly something that people worry about, right? So many reasons we might do this. And so, you have these schemes that people are starting to develop and deploy at, Google, Apple, wherever, where you've got some central model you're trying to fit, and you have a bunch of devices in people's pockets, and so the central model sends out some model to device 1. Device 1 does some kind of processing or something like that, and then sends back some update to the model. It says you should change your model this way to make it fit my data a little bit better. We keep iterating this back and forth, right? But of course, what you really want to do is make each of these kind of updates or changes to the central model private in some way. Right? So these are the types of scenarios that we really are looking to apply these types of ideas. Okay. Okay. All right. So now this was once a provocative question. It might still be provocative in Massachusetts. In California, it's not because you can smoke weed wherever, whenever. My next door neighbors do it all day, every day, which is great for my 3-year-old. She's stoned most of the time. But, whatever. So anyway, so once this was a provocative question, so you can ask, okay, have you ever smoked marijuana? And now I'm embarrassed. I don't want to answer this question to you guys, or maybe I do. But what I'm going to do, I'm going to take this die, and I'm going to roll it. And if it's a 1, 2, 3, or a 4, I'll tell you the truth. And if it's a 5 or a 6, I'm going to lie to you, okay? Okay? So have I ever smoked marijuana? So 5 and 6 is lie, 1, 2, 3, 4 is tell the truth. I have never smoked marijuana. Okay?
1, 2, 3, 4.
What?
1, 2, 3, 4.
So now you don't know whether I actually have or not. You get a little bit of information this way, but still you're like, okay, has John actually ever smoked marijuana? You have no real idea, right? I mean, maybe if you know me well, you do know the answer to this question, but most of you probably don't. Right? But it turns out that scheme for where I roll this die and then answer truthfully or lie with some probabilities is actually optimal for trying to figure out the number of people who have smoked marijuana or done a drug or something like this. Okay, you can't do better than that. All right, so when is it optimal? So the model we're going to use is local differential privacy now. So what we're going to have is, as I said, we have x. It goes through this channel, q of z given x. And we're going to say this channel is differentially private if for all sets A and for all possible input data points x or x prime, the probability that the output belongs to set A given x or x prime is less than e to the epsilon. All right, and sort of the standard recommendation from differential privacy folks is that you want epsilon to be something like 1 or a little bit less than 1 or so. All right, because that says that basically in terms of testing, it says that your probability of making a mistake is going to be at least about a third. Right? So this is our definition of privacy now, is each individual one of these channels is going to be differentially private. Okay. And it turns out that we can actually, I'm going to present a bunch of results on optimality under differential privacy. It turns out that all of our results actually extend to a weaker model where it's not that you always have to have this ratio, just that for every x and x prime, that on average the ratio of your densities is less than e to the epsilon. Okay, so you don't need to have it holding uniformly. As long as it holds on average, all of our results will still be true with slightly tweaked constants, but they will still just hold. Nothing's going to change.
Sorry, so this is for all x in expectation with respect to x prime independent. So what is this?
What does this mean? What is this? This is saying that Okay, so here what I've done, but this is basically saying that the integral, so let's say that Q has density little q. This is saying that the expectation for z drawn according to q of whatever given x of the ratio of these densities, q of z given x divided by q of z given x prime, is less than or equal to e to the epsilon for all x and x prime. Is that OK? Yeah, the notation's a little bit wonky. So this is just what I'm saying. Is that on average, the ratio of their densities is less than e to the epsilon, which of course is a little bit weaker than the ratio is always less than epsilon. David?
And we're assuming that we know Q?
Well, I'm going to get to choose Q, right? So the game is, I'm going to design Q so that it satisfies this constraint.
And then you tell you tell each phone what the Q is that they're allowed to use.
Yeah, I'm going to hand you this die, and I'm going to say, David, roll this. If it's a 1, 2, 3, or 4, tell me the truth. If it's a 5 or a 6, you're going to lie to me. And now don't let me see you roll it. And then I'm going to ask you, David, have you ever smoked weed, right? Or something like that. So that's the situation that we're thinking about. So in terms of if you were thinking about, OK, I'm going to fit a model in some distributed way, what this means is I'm going to release the source code to my model fitting scheme. And then some security researcher or whatever can look at my code and be like, yep, that is private. I mean, probably what would happen is a security researcher looks at my code and is like, I broke it, right? And then you iterate, and then they break it again, and you iterate, and they break it again. And you constantly get sued for breaking people's privacy. But that's, let's pretend I could write secure code, and you could verify that it was secure, right? I know security researchers, right? This is what they do. I mean, have you guys ever met Dan Bonet? Like he just breaks things. That's his job. It's amazing. It's also disturbing how insecure all of our data is. But anyway, so we can tweak it to this model. All of our results will still go through. OK, so let me give a little vignette just to kind of motivate this. Like why, so I'm going to try to develop optimal schemes under these kinds of constraints, either differential privacy or this kind of averaged version of differential privacy. So here's a funny vignette. So let's suppose I wanted to estimate the median salary of, say, all the employees in the University of California school system. OK? So I have a bunch of data X, and I want to estimate the median salary. All right. So what might you do? Well, one thing you might do is say, OK, I'm going to take all my individuals. I'm going to take each individual's salary. I'm going to add a boatload of noise to each one of them. OK, and then I'm going to just take the median of that. And as long as this noise has median 0, is symmetric, then this will eventually give me the right answer. Right? Seems kind of reasonable. OK, here's a much, much better procedure. OK, what I'm going to do is I'm going to go around this room. I'm going to have a current guess of what the median salary is. I'm going to just ask each of you, is your salary bigger than whatever, x or theta, my current estimate of the median? And I'm going to let you lie to me with some probability, but you're going to just say yes or no. OK? You're going to flip a coin, and if it's heads, you say the truth. If it's tails, you lie to me. And then what I'm going to do is, based on whether you said up or down, I'm going to update my guess of the median salary. OK? Now let's take a look at how these two things perform. So I'm going to have one where I add a bunch of noise to my individuals, and I'm going to have this where I just say yes, no, your salary is above or below this. And each of them will provide the same exact privacy guarantees. OK? So here's this naive estimator where I've added a bunch of noise. It gets to see the entire sample with noise added. So that's 250,000 employees. This is actually all the employees of the UC, University of California school system. And for whatever privacy guarantee I'm providing, I think I used epsilon equals 1. It's got an error of about $1,000 in terms of median salary. OK, so you're about $1,000 off. With this scheme of is your salary higher or lower, you go through, and after observing, I don't know, a couple hundred people, your error is much lower. After observing, say, 50,000 employees, of the 250,000, your error is on the order of about $10. Maybe $20 or something like that. But it's basically, there's 2 orders of magnitude difference here. By the time you're out here, you get the whole employees, you're off by $1. Right? So you're off by $1 versus $1,000. So you've got a 3 magnitude. Oh, the yellow line is confidence intervals. So this is, I ran the experiment like a couple hundred times, and these are 95% confidence intervals on our estimator. Yeah, but it's a log scale, which is why it drops down so much, because sometimes you're actually within like a couple pennies. So that's a confidence set. There is a confidence set on this one. It just always sucks. Okay, the green line is the confidence region band for this, and it's always off by a couple $1,000s, right? So being a little bit more intelligent, probably a reasonable idea. You're doing a lot better in one versus the other. Yeah.
This is very confusing. So the naive one is systematically biased.
No. It's just always wrong. This is the absolute error. It's absolute error.
How can it do that? I mean,
How can its absolute error?
the sample size goes to infinity, it can just not work.
No, the sample size is 250,000. I just gave it 250,000. I gave the naive estimator. Sorry. Yes. Only one of these is a function of the x-axis of the horizontal axis. That's the blue line. I gave it 250,000 observations, and then I'm just putting the line here. So really, it should just be a point right here. Yes, it should just be a point right here. It would, if I only gave it a few, it would be up here somewhere. It'd be terrible. Yeah, but then it just looks even worse. So I thought I'd be slightly nice to it. Let it have the whole data, and then you can look at it. All right, so some carefulness in terms of how you develop these schemes can give you substantial benefits. Okay. All right, so I've made these claims about, okay, we want to develop optimal algorithms, blah, 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 blah. So the question is, how do you define optimality? So let's dig into this. So one classical way of defining optimality, sorry. Yeah, Sasha.
They have same differential privacy as in terms of same upper bound that you were able to derive, or you have lower bound in both schemes?
They have exactly the same differential privacy in the sense that they both have the same upper bound. There is also there is an associated lower bound, which would probably be a little bit lower than this, but it's not much. I mean, there is a lower bound on the privacy this provides versus what this is providing, and they're still very close. Yeah. So it's a fair experiment. I'm not handicapping this for no reason.
So
Philippe.
when you do the naive scheme, you actually observe just a convolution of the distribution you're interested in with something else, and you could potentially extract a bunch of statistics from this convolved by just deconvolving and just querying whatever you want.
You can,
Is
yes.
the optimal scheme that you have allowing you to do this, or it's like completely tailored to spitting out the median?
The optimal scheme?
Can you put the naive algorithm back up?
Yeah.
So you see, right, so if you actually give me the Z1 to Zn from the naive scheme,
Mm-hmm.
I can do a bunch of things. And
Yeah.
in particular, I can compute their median. If you give me this thing, can I do whatever I want? Like, can I actually get the interquartile range divided?
No.
by,
It's designed for, yes. So I have designed this for this
So
application.
is there a sense according to which the naive scheme is optimal in a uniform sense?
In the sense that I can maybe
That
do
what
some
you want to
other,
estimate is the distribution.
yeah. So there are results that I'm not going to get into which say, you could either have a mechanism or a scheme or a channel designed for your problem at hand, or you could have a channel that says, okay, you want to estimate, I'm going to just give you a big data set, and you're going to use it later to do whatever you want, right? So you're going to allow further downstream applications. Turns out there's a huge separation between those. I don't remember the exact separation off the top of my head, but basically, if you want to have something that you can use downstream for many other tasks, then you're going to suffer hugely for most of them. It's basically going to be not useful. So that's why we typically stick with, okay, let's try to figure out, I have a problem at hand, how can I solve this problem? And that, if you're actually doing...
When it comes to privacy, maybe today you want to learn my median, but maybe tomorrow you will learn something else, and then you will just query again and again, and maybe you will actually hurt my privacy.
Yes, that is totally true. Yeah, so today I want to learn your median, tomorrow I want to learn your mean, and on Wednesday next week I want to learn, what glasses prescription you have, right? So I'm going to issue different queries to you. And so there are two answers to that, and one is that, one answer to that is that, that's why we have these guarantees that when you issue people multiple queries, they still provide some privacy protections. It doesn't degrade just instantly, it degrades slowly. So that's one answer. Answer two is that if you're ever actually implementing these, you need some kind of legal stricture beyond kind of the statistical or machine learning or whatever thing you're doing that says you can't query people more than X times per hour, day, year, whatever. And then you provide some kind of global guarantee that says within a year, this is how much privacy I'm going to compromise. And like, I certify that I'm not going to do that. And there's a law or whatever. There's some contract that says you can't do that. But yeah, there have to be, I mean, there are two sides to this. There's the mathematical side, and then there's the like, how do you actually do this in practice? And they're both important. And I'm not going to touch the how you enforce people only querying you 2 times or 3 times in a day. But it's important. All right. So going back to our original question, we wanted to know what are the trade-offs between privacy and estimation, right? So another way to write this is if I give you a sample of size n, how does my risk, how does my loss, how does my performance change with n? OK, so kind of the classic way of assessing optimality or risk of a procedure is what's known as the minimax principle. OK, so the game is we have some parameter, theta of p. P is my population distribution. And I want to estimate this parameter. And I have some loss, L, whatever it is, that measures my error. And I'm going to define the risk, excuse me, of my estimator, theta hat, for whatever population distribution P, probability distribution I have, to be the expected loss of my estimator, theta hat, when P is the true distribution. And then the minimax principle says that, well, we'll measure the quality of an estimator by looking at its worst case risk. So I look at some family of possible populations, and I say I want estimators that do well for any possible population I might get. Let's measure things as the supremum risk. OK. So that's the minimax principle. Choose an estimator that tries to minimize this. And so what we can, the first thing you might do is say, well, let's build on this minimax principle and try to do it for privacy. So you start off with your minimax risk, right? You have your family of distributions P, some loss, and your parameter that you care about estimating. The minimax risk, given a sample of size n, is you say, OK, let's look at the worst case expected loss. And then we're going to take the best estimator for this worst case loss. Right. And then if you wanted to do this with privacy, well, what you do is you basically pick some collection of private channels Q, sub epsilon. So epsilon's our privacy level. So this would be like all possible sampling schemes like this that satisfy whatever definition of privacy we're using. And then we say, let's put that in here. And we also want to have the best possible sampling scheme Q that respects our privacy guarantees. Right? So we started with minimax. We introduced family of channels. And we look at the private minimax risk. So worst case distribution, then best case estimator, and best case private channel. So that's one way of deciding, OK, this is an optimal set of estimators. Right? And so with Mike Jordan and Martin Wainwright, we did, I've done a bunch of work sort of kind of characterizing this behavior, trying to understand it. Right? So the issue, there's a big issue with minimax, which is that it's kind of too conservative and potentially too imprecise. Right? So here's basically the result. Roughly, if you want to achieve a particular error in your estimator, and you want it to be some fixed error, then a private estimator needs a sample size that scales like multiplicatively in the dimension larger. So if you want to estimate a 5-dimensional parameter, you need a sample size that's 5 times what a non-private estimator would do. If you want to estimate a 100-dimensional parameter, you need 100 times the sample size. So this is kind of not great, right? So that's a little conservative. I mean, more generally, it's not like you necessarily actually have a worst case problem when you get a data set, right? You might not have a worst case problem. Maybe it's an easy problem. So one of the big criticisms of kind of this minimax viewpoint is basically it tells us nothing about the difficulty of the problem I actually have, right? I don't care about the worst problem. How hard is the problem in my hand? How hard is this particular instance? All right? And this is what I'd like to try to understand now, is how do we try to understand how hard is the problem that I hand you, right? Because that's what we want. All right, so let's talk about, well, how would we know, if I tell you I'm going to derive some lower bounds on the possible quality of estimators or some kind of optimality results, how do we know that we've got a fully satisfying kind of guarantee or a fully satisfying lower bound? I would postulate that there are basically 3 desiderata you want. Okay, so number 1, it should be distribution specific or instance specific. So whatever population you have, whatever actual problem you have, you're measuring like the difficulty of that problem. It should be uniformly achievable in that there are estimators that exist that can adapt to your sort of measure of problem difficulty. So whatever problem you have, they do as well as you could do for that problem. And then 3, what you want is what I'll call a super efficiency result. So this is how you know you've gotten it right. What that says is if I come to you and say, here's a lower bound on how hard it is to solve this problem, right? You could say, well, here's an estimator and it does better than your lower bound, right? So here's a stupid example. Like, suppose my estimator outputs 0 all the time, and I want to estimate the mean of some distribution, right? If the mean of the distribution is 0, that's a really good estimator. Yeah? If the mean of the distribution is not 0, my estimator, not so good. Okay? So you want a super efficiency result, which says basically that if you come to me and say, hey, I can beat your lower bound on this distribution, on this population, well, then I can tell you, actually, well, there's another problem, another distribution where your estimator is really terrible, right? Like, so if your estimator is output 0 all the time, I can very easily find examples where your estimator is not very good. So if we can have all 3 of these things, then we're like, OK, yeah, we've nailed a lower bound. This is like really totally satisfying. Do these 3 make sense? Does anybody have questions here? Because this is not completely standard in terms of the types of optimality results that we often see in statistics or machine learning. Would anybody be unsatisfied if I gave them a lower bound that satisfied these 3? You'd be satisfied? Guy, would you be satisfied if I? Yeah, sure. Yeah, sure. You're too easy. All right. OK. So in this case, there's sort of a classical approach that starts to get at this. And this classical approach is what's known as hardest. You start asking what are called hardest one-dimensional subproblems. Okay, so you take whatever problem you have, and then you look at kind of the hardest perturbation to that problem. And this actually started off with a paper by Stein in '56. So if you're familiar with the history of statistics, you see Stein 56 and you think James Stein estimators, but it's not that paper. It's another paper that I think deserves to be just as well known because it influenced basically this huge line of work on semi-parametric estimators. So here's Charles Stein. As all good ideas in statistics, it came from Stanford. You guys don't even push back against that. That's good. Just lay down. There's Charles. This was a paper at the Berkeley Symposium called Efficient Non-Parametric Testing and Estimation. And if you kind of dig into this, basically what he's saying is, suppose one wants to estimate a particular real-valued function of some population, then basically it is often the case that there is a one-dimensional problem, not some kind of infinite-dimensional population problem, but a one-dimensional problem that is at least as difficult as the whole problem you care about. Okay, so you can reduce hard, maybe potentially infinite-dimensional problems. If all you care about is a one function, you can reduce them to one-dimensional optimization problems or estimation problems. Right? So we're going to take this idea and run with it. All right, so you start off, you say, OK, well, minimax looks at worst-case populations P. What this local minimax, or hardest one-dimensional subproblem, does is it says, OK, we're going to start with some fixed initial distribution P0. And then what we're going to look for is one alternative distribution to P0 and look for the single worst one. OK, so we go from worst case to saying fixing this distribution P0, which is like your problem at hand. OK, and then I'm going to look for the worst other possible distribution. And then my estimator gets to know, hey, the data is either P0 or P1. It's a one-dimensional problem. You just have to decide, was it P0, was it P1? And we're going to look at the worst risk between P0 and P1. OK? So we go from worst case to just hardest single problem between P0 and P1. Right? Yeah?
How did it go from inf soup to soup?
Yeah, well, I mean, I can write any formula I want. So I was like working in LaTeX, and it was \soup and then \inf. But so this is the minimax approach. But now we're saying, OK, you know what? We're gonna go away from minimax. We're going to follow Charles and say, OK, we're going to look for the hardest one-dimensional problem. So we're going to just look for a pair of problems, pair of points that are hard to distinguish. So instead of inf soup, we're going to go from, basically, we still have a kind of a soup. It's just a max between two things, right? So this, of course, this is always going to be less than this quantity, right? because I moved the whole soup outside. But I'm looking just what's the hardest single alternative? What's the hardest local alternative to my problem? Okay, so I have my problem at hand. What's the hardest alternative to it? And then we ask, what's the best estimator for this?
Where does P0 come from?
P0 is whatever problem you actually have. You know, it's like the true distribution of data that you're observing, right? Because there is some problem you have. You have a problem, and the question is, how hard is this problem? Yash?
Does script depend on P0?
I mean, script P is kind of like, what's the set of possible populations you could be observing from? So let me give, well, we'll get, sorry, go ahead.
Wait, then why is it, I mean, the hardest problem,
Let me give it.
okay.
Let me give a really simple example, because maybe this will make it a bit clearer. And I'm going to go through this example again later, but we can talk about it a tiny bit now. So let's just say I want to estimate the parameter of a Bernoulli distribution. I have a Bernoulli P. OK? So then the set of possible distributions, P, is equal to all Bernoullis with some parameter P prime, where P prime is in 0, 1. Right? Okay? But like when you're, you've got some coin, it's one particular coin, and it has a particular probability of being heads. That's your P0. You're going to keep flipping that, right? And then the question is, how hard is it to estimate that Bernoulli distribution? And we know that if you take the sample mean of a coin flipped a bunch of times, then of course, expectation of x bar n minus p squared is going to be equal to p times 1 minus p divided by n, right? So the problem is estimate a Bernoulli p. The difficulty is p times 1 minus p over n, right? The hardest Bernoulli to estimate is going to be to set p equals a half. But if you happen to get a really biased coin, it's pretty easy to estimate like what its probability is. And if you substitute this in here and do calculations, you will literally get out this exact quantity, maybe modulo a numerical constant. Okay? Does that make it a bit clearer? So this is the actual thing I've got. This would be my whole family. The question is, how hard is it to estimate the parameter of the Bernoulli that I'm handing you? All right. Okay, so there are a bunch of standard results in this regime. It turns out that this is the This is the framework that gets you the classical information bounds. Like if you took introductory statistics or whatever, and they said, hey, the Fisher information is a thing, and your efficiency of estimation is bounded below by the inverse Fisher information, well, this is what gives you that. This gives rise to those kind of calculations. It just spits them out. We could go through this if you want. I can do whole lectures on this stuff, but we probably don't have time for that right now. And it's spitting in high dimensions. If you want to estimate some linear function of a parameter, say in squared error, then you get V transpose inverse Fisher information. You get all of the classical Fisher information type results in your kind of classical problems. It just gives you the right answers here. Okay, so this is what actually gives rise to a lot of the optimality theory and classical statistics. Okay, so we've got our local minimax complexity. Well, we're going to do the privacy thing again, and we're just going to say, okay, local private minimax is for this population P0. Let's look at the worst alternative for the best possible private channel, and we're going to calculate this thing. Okay? Okay, now what we can ask is, how should we actually expect to control this quantity? And I'm going to give you the answer to this. And it comes out of basically some functional analysis you can do. So let's take a quick step back. The modulus of continuity of some parameter I care about with respect to some metric d on distributions is if I fix delta, and I say, OK, I'm going to look at any two pairs of distributions, P0 and P1, how much can my parameter change when I keep these two distributions close together? That's the modulus of continuity. So if you take functional analysis or just basic analysis, you've seen this type of quantity. So the idea is basically, how much does a parameter change for small changes in my distribution? And if this number is big, it should be hard to estimate, because you tweak your distribution a tiny bit, your parameter hugely changes, probably hard to estimate. So this is kind of the picture. If this is delta, here's your parameter on the vertical axis. Here's distributional changes on this axis. If the slope of this is small, it's easy to estimate. You can't change much even if your distributions are different. Over here, your distribution changes wildly, or your parameter changes wildly even for small changes in distribution. Hard to estimate. Okay? So then there's a beautiful set of work known as geometrizing rates of convergence in the late 80s, early 90s by Donahoe and Liu, which basically says that in a minimax sense, this quantity literally characterizes estimation, okay? At least in a worst case sense. And given that we're running out of time a little bit, I'm going to kind of just say we know this does it in classical statistics. It nails it. And so now we're going to do it for the privacy setting, okay? But instead of the global modulus of continuity, we're going to just ask for the local modulus of continuity. So at P0, my population that I've got, this Bernoulli P, how much can my estimation, my parameter change with small changes to the underlying distribution? So how much does the parameter change when I change the distribution a little bit in a neighborhood of P0? And so there's been some work in the last couple of years, some by Kai and Low on estimating convex functions, some by Sabyasachi Chatterjee, John Lafferty, Yuancheng Zhu, and I on stochastic optimization, where we use these ideas to characterize difficulty. OK, so in the private case, it turns out that what governs everything is what's known as the modulus of continuity with respect to total variation distance. So I take my initial distribution P0. I say, OK, how much can I move my parameter of interest while keeping the distribution close to my initial distribution, my population, in variation distance? And here's the theorem that you can show, is that this local minimax complexity is upper and lower bounded as long as our privacy parameter is sort of less than or equal to 1 or so by the modulus of continuity of a constant divided by square root n epsilon squared. So we can completely characterize this by this modulus of continuity. So this is how hard these problems are. And I claim that this actually satisfies all of the desiderata we wanted. And I'll show you a little bit about that shortly. Yash? Right, so this is why I said when epsilon is like order 1. Yeah, so when epsilon is bigger than 1, you actually need a whole different set of calculations. And for reasons, that's an interesting question. Like, what should happen? Should we allow epsilon bigger than 1? There's all sorts of questions there. The differential privacy community has never they always say, oh, epsilon bigger than 1 doesn't count, not private. But there are reasons that you might want to get to that. Specifically, that it turns out that these numbers are typically too large to actually allow effective estimation. Let me give some examples of what happens with this. So here's a funny one. So here's this Bernoulli example again. Non-private mean, sample mean is always p times 1 minus p over n. The smaller p is, the easier things get. Turns out in the private case, I give you a Bernoulli p. Well, the variation distance between p0 and p1 for Bernoulli p plus delta is always exactly delta, right? That's the variation distance. So it turns out, well, if the modulus of continuity is based on delta, local minimax lower bound for the private case is always 1 over n epsilon squared, no matter what. Doesn't matter what your population is, it's always going to be as bad as it could possibly be. You can't be adaptive to the easiness of a problem. You look at this and you're like, OK, fine, who cares? I can estimate a coin. 1 on n is pretty close to p times 1 minus p on n. I don't give a crap. And you're like, OK, fine. Now let's suppose you're a large internet company and you want to fit a classifier, right? So we know from deep learning that it's really easy to get very highly accurate classifiers, and so we should be able to do it. OK, let's do a logistic regression problem. OK, I just want to predict the label plus minus 1. We're going to do a one-dimensional logistic regression problem. These are pretty easy, right? So I have some parameter. It's the true parameter theta 0. The bigger theta 0 is, it's the easier the problem is, right? Because if theta 0 has a large magnitude, this quantity will always be close to either 1 or 0. Super easy, right? OK, so I just want to make predictions. I don't care about inferring the parameter because I'm a predictor. I just want to know, is Sasha going to click on this ad? That's all I want to know, because I want to sell him a coffee machine, because I know I'm going to make a lot of money when I sell him an espresso machine, right? So I do that. OK, so then if we don't have any privacy, and so I just want to measure error in terms of my predictions. Right, I'm just going to ask, OK, you have an estimated p hat. It's the probability that Sasha clicks on this ad for a coffee machine versus the true probabilities. And if you just use the maximum likelihood estimator, then roughly, you do some calculations. Roughly what you see is that the bigger this parameter theta 0 is, the easier the problem is. So if it's an easy problem to classify, you can learn that more quickly, right? So, and it's actually exponentially faster. The easier it is, the exponentially quicker you can learn this. In the private case, because of this variation distance modulus of continuity, the lower bound is always 1 on square root n epsilon squared. So even if you had an easy problem, in the non-private case, it doesn't get easy. There can be an exponential gap between these. So, this Bernoulli thing, you were like, I don't care. But now all of a sudden you're like, oh, I can't actually learn when people are going to click on ads. Like, that starts to get to be a little bit of a problem. And then, now Google really wants to compromise your privacy, because if they don't, they can't sell you lots of good stuff and print money, right? So anyway, so that's whoopsie.
So to apply the previous theorem in this setting,
Mm-hmm.
is there a distribution over x's? What is the...
Oh, yeah, sorry. So I'm sorry. I was being a tiny bit cavalier here. Yeah, my x's are just uniform plus minus 1. I choose x uniformly and plus minus 1. And then y is just drawn conditionally on x according to this model. Yeah, sorry. We could do different distributions, but to get this very clean characterization, we just make our lives easy. We can do other ones, but it's kind of the same story. All right, so just a real quick aside, I said, okay, a satisfying lower bound should have the super efficiency result. So we can actually prove that if you have an estimator that's delta times better than what I say you can be, I can come up with another distribution, and your risk is going to be at least a factor of log 1 on delta worse. Okay, so you have to do worse somewhere else. If you do better in one place, I can give you a population where you have to be bad. Okay, so you can never beat my lower bound really is the right lower bound. If you beat it, you have to be worse for some other problem. There are other populations you can't do well on. Okay, so anyway, so I'm running a little low on time, so I think what I'll do is just say, okay, there are some dimensionality issues still, even in these local complexity results. I'm going to jump through this really fast, but let's, okay, blah, 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 blah. Okay, let me give one little vignette on experiments, and then we will call it a day. Oh, David, sorry.
Something really big. Did you ever say what Q was?
Did I ever say what Q was?
Yeah.
These are lower bounds, so this applies for any Q. Best possible Q. I don't care what Q you choose. No channel is going to allow you to estimate this better than this.
The original part of the talk, right? So what's the minimax or under this definition optimal approach?
Oh, what's the optimal approach? Yeah, they're pretty sophisticated.
And is that part of your paper?
Yes, that's in the paper, and actually it's also right here. But given that it's noon and people are probably hungry, I'm not going to go through it too much, if that's okay. But effectively, whatever. Well, yes, it's in the paper, but let's punt on it right now.
Is it a limit on time?
Oh yeah, no, they're super efficient. They're really easy to. They're actually quite easy to implement. I mean, it's basically computing means in a clever way. So there's no computational issues in what we're doing. Okay, but let me give you a vignette just to kind of show, okay, you can kind of do some of this, and it's not as bad as all that. So here's a flow cytometry experiment. I have 11 proteins that I'm measuring on 7,500 cells. I want to understand how the proteins interact, so infer something about the network structure. I'm going to model this with a Gaussian graphical model, and I want to ask, what are the individual parameters in this? I just care, is protein 1 interacting with protein 2? Do they have some kind of regulatory interaction? That's the kind of thing I care about, just single pair interactions. And so we have what I call a one-step procedure, which is basically this locally optimal procedure that's adaptive to your problem and still private, versus like the classic minimax optimal, worst case optimal procedures that I designed a couple years back. And I'm going to just put this plot on. Okay, so what is this showing? On this axis is our error in estimating a parameter of these models. And on this, and then this is a count of how many times our error belonged to a particular bucket. Okay, so the blue is the non-private estimator. Okay, so typically it has errors that are very small in the neighborhood of, say, minus 0.02 to 0.02. That's where its errors are all clustered, so not too much error. The black is this kind of locally optimal thing, trying to adapt to the difficulty of the problem at hand. And you can see the errors here are not as good as the non-private scheme, but they're kind of clustered in a neighborhood. And then if you have try to just optimize for worst case behavior, then you just get these very wide tails. You are much less accurate than you want to be. That being said, this is still definitely not as good as being non-private. All right, so further questions. Things are kind of looking pretty grim. Like you looked at that logistic regression example, it never got easy. you might ask yourself, well, what are we supposed to do here? Maybe we can change the kind of protections that we provide people. Like, I don't care, adversaries don't know that it's literally me or Sasha. They're just trying to reconstruct information about us. So maybe I just want to protect against like you being able to reconstruct everything about me without knowing who I am a priori. Maybe that changes things. It turns out that it does. We're currently writing a paper on that. And the practical use cases that Guy wanted to hear about, that's also coming very soon. We have the experiments, we just don't have the paper written. So there are ways to tweak these things. Anyway, so here are some references. I really appreciate your attention, and happy to take more questions or call it a day.